Does anybody know of someone who you know is coming but is not here yet? I hear footfalls. I'm glad you all could come this afternoon amid what, as has been said, is a busy time of the semester, and particularly several other things going on this afternoon. Welcome. We're also pleased to have with us Xinchuang Dong of Qingdao University, who'll talk about admissibility analysis and synthesis of singular systems via delta operator method, and we look forward to hearing it.
It's my great pleasure to be here to present my work, and thanks for the opportunity. The title of my report is Admissibility Analysis and Synthesis of Singular Systems via Delta Operator Method. This work is supported by the National Natural Science Foundation of China, and the name of our project is Performance Analysis and Synthesis of singular systems based on Delta operator model. Singular systems are compared to normal systems. First, we'll show the difference between singular systems and normal systems from mathematical forms. We consider a very simple control system. Assume the system to be linear, continuous, and time invariant. If it is a normal system, then it can be described by the equation A. If it is a singular system, then it can be described by the equation B. The difference is that here is a singular square matrix. Because of the distance of a singular matrix, it's difficult to guarantee the existence and uniqueness of a solution to singular systems. It's a challenging problem to solve a singular system to admit a unique solution. Let's see some examples. First, we consider a simple circuit network. It's a RLC network. We use V to stand for the voltage, and then it's easy for us to obtain all the relations in the network. All the relations in the network can be described by the four equations. And if we select x, u, and y this way, then we can rewrite the above network as the two equations. Here, we only care about the matrix E. And from the expression of E, we can see that E is a singular square matrix. In this case, the above network can be expressed as a singular continuous system. Let's see another example. The fundamental dynamic relative model of economic systems can be given as this equation. Here, all the terms in the equation all have definite physical meanings, such as sk, a, ask, b, and dk. Here, we only care about the matrix B, and B is the capital coefficient matrix. And we can rewrite the above equation as another way. It's a difference equation. And it should be noticed that in multi-sector economic systems, production augmentation in one sector doesn't need the investment from all other sectors. And in practical cases, only a few sectors can offer investment in capital to other sectors. So in this case, most of the elements in the matrix B are zero, except for a few. So B is often a singular system. In this case, the above system can be described as a singular discrete system. According to the research content of our project, we have carried out a series of research and have obtained some valuable results. We have solved the problems of critical analysis, observability analysis, and admissibility analysis. We also have derived some solutions to the problem of admissible control. Besides the above results, our work also involves some other aspects, such as intrinsic control, passivity analysis, and pole assignment. In this report, I only want to introduce some of our results. That is, I only want to introduce the results in the following two episodes. One is about admissibility analysis, and the other is about admissible control. The outline of my report is as follows. First, I'll give some introduction, and next, I'll set up the adult object model for singular systems, and next, I'll present our solutions to the problems of admissibility analysis and admissible control. And finally, I'll provide some examples and then draw some conclusions. First, let's see introduction. Normal systems are also called state systems. They can only describe dynamic histories in control systems. Dynamic histories can be described as differential equations for the continuous case or difference equations for the discrete case. Singular systems also have many other names, such as discrete systems, implicit systems, and so on. Compared with normal systems, singular systems can describe not only dynamic histories, but also algebraic histories. And algebraic histories can be described as algebraic equations. We can find many applications of singular systems, such as large-scale systems, nuclear reactors, pastry, robots, and so on. Besides the above practical background of singular systems, singular system methods are also adopted to study normal systems so as to get less conservative theoretical results. It's to be noticed that singular systems are essentially different from normal systems. Here we only use mode as an example. Mode is a definition in control theory which is used to discuss the solutions to control systems. We also consider a linear, continuous, and time environment control system. And A express a normal system. B express a singular system. For the system A, it only contains one kind of modes. It only contains finite dynamic modes. But for the system B, it usually contains three kinds of modes. They are finite dynamic modes, infinite dynamic modes, and non-dynamic modes. The existence of infinite dynamic modes and non-dynamic modes make it hard to guarantee the existence and the uniqueness of the solution to the system B. And even if a solution indeed exists, it may have undesired impulsive behavior. So studying singular systems is much more complicated than that of normal systems. Here we only care about the most fundamental requirement in control systems. For normal systems, the requirement is just stability. But for singular systems, the requirement is admissibility. And admissibility is composed of three parts. For the continuous case, admissibility includes stability, regularity, and non-impulsiveness. For the discrete case, admissibility includes stability, regularity, and causality. Here, stability is the same as that in normal systems, and regularity is the condition to install the existence and the uniqueness of a solution to a singular system. And non-impulsiveness means that there is no impulsive behavior in the solution. And causality means that the solution can be determined completely by the current and the formal information of the system. If a singular discrete system is regular but not causal, then some part of the solution will depend on the future information of the system, and such a system cannot be realized in practice. We have found many research about singular systems. Here I just list some monographs published in spring from 1989 to last year. Besides this monograph, we can also find many other monographs, and we can also find many articles in different journals and in different conferences. Control systems can be divided into continuous systems and discrete systems. As to discrete systems, some systems are naturally discrete, such as economic systems, but most discrete systems are obtained from continuous systems by sampling. They are described by system operator and therefore have numerical yield condition. The numerical yield condition is that when the sampling period tends to 0, a discrete system doesn't tend to the corresponding continuous system. And here we will show how to get a normal discrete system. Given a normal continuous system expressed by the equation C, and we select a positive scalar h as the sampling period, and then we can get the discrete model of the system C. It is described by the equation D. And here, Q means the system operator, and it is defined this way. And AQ, BQ can be obtained from the equation C, and AQ, BQ can be obtained from AS, BS, and H. Then from the expression of AQ and BQ, we can see that when H tends to 0, AQ doesn't tend to AS, and BQ doesn't tend to BS. This is the yield condition. In order to avoid the above problem, Goodwin proposed a dot operator, and the dot operator is defined in this way. So we can see that when H isn't 0, we can obtain the relation between dot operator and the system operator as this way. So for the same normal continuous system, we can obtain its dot operator model as described by the equation D. And A dot, B dot can be obtained from AQ, BQ, and H. They can also obtain from H, AS, and PS. And from the expression of A dot and B dot, we can see that when H tends to 0, A dot will tend to AS, B dot will tend to BS. Compared with system operator, we can find the following advantages of that operator. First, we can see easily that it can provide a theoretically unified framework of normal continuous systems and normal discrete systems. And next, we can see that it pertains the information of sampling period explicit. Besides the above advantages in theoretical aspects, we can also find some other aspects, some other advantages of that operator in practice. For example, it requires smaller wavelengths and it has better numerical properties at high sampling rate. Here are the research about that operational method. Here are the 3 monographs that we know, and we can also find new articles. According to the research about singular systems and the third operational method, we found some fundamental problems. They are as follows. First, the existing results about third operational method are all in the framework of normal systems. And second, the existing results about singular systems mainly consider singular continuous systems and singular discrete systems separately and independently. And no research results considers studying singular systems through third operational method. So it's natural for us to ask the following questions. Whether can we introduce third operator into singular systems? Can we set up a suitable third operator model to unify a singular continuous system and its discrete model? Can the performance analysis results of singular third operator systems unify the existing corresponding results of singular continuous systems and the singular discrete systems? And can the control design methods for SDOS be applied directly to singular continuous systems and the singular discrete systems? According to our research during the past 2 years, we can say yes to all of the above questions. So next, we'll introduce our answers to the above questions one by one. First, we'll set up the third operator model for singular systems. Consider a singular continuous system described by the equation 1, where ft is the state, ut is the control input, and E is a square singular matrix. We assume that the rank of E is R, which is less than n. And since the rank of E is R, irreducible matrices M and N can always be found such that MEN is E bar, which has a special structure. And we use MN to define other matrices such as A bar, B bar, and X bar T. In this way, we can observe that the system 1 is equivalent to the system 2, and which is the same as the system 3. And then we select a positive scalar as the sampling parent and discretize the above system 3. And as to the system 3, to the first equation, it's a normal continuous system. We can use the method that we have introduced before to discretize this equation. As to the second equation, it's an algebraic equation. We just multiply h to both sides of this equation. So we can obtain the discrete model of the system 3 as the system 4. And the system 4 is also equivalent to the system 6. The system 6 is just the discrete model of the system 1. And next, we introduce some matrices. We denote E inactive, defined in this way. And from the definition, we can observe that E inactive satisfies parallel small equations 1 and 2, which means that E inactive is a 1-2 inverse of the matrix E. And based on E inactive, we define another matrix, ASE. And from this definition, we can obtain that ASE satisfies this equation. And we also introduce a matrix function percent A, which is defined for a correct graph scalar H and the square matrix A. And then from above we can obtain that percent A and B have this form. And from above we can obtain the relation EQ, BQ, and AS, BS. This relation effect describes the relation between the singular continuous system 1, and its discrete model. And from the discrete model 6, we can get the derived model of the system 1 as the system 10, where A dot, B dot can be obtained from AQ, BQ, E, and H. A dot, B dot can also be obtained from AS, BS, E, and H. And now we use the definition of percent A, and finally we can obtain the following result. We can find that when H tends to 0, AQ will tend to E, BQ will tend to 0, and A dot will tend to AS, B dot will tend to BS, which means that the discrete model 6 of the system 1 still has the Young condition, but the delta-oriented model of the system 1 will tend to the corresponding singular continuous system, system 1. Here we show the relations among singular systems. And this is a singular continuous system. And from this relation, we can derive its discrete model. And from this relation, we can derive its delta-oriented model. And when H tends to 0 from the same relation, we can also obtain the corresponding singular continuous system from its delta-oriented model. As to the discrete model and the delta-oriented model, they have very direct and simple relation as this. So from this diagram, we can see clearly that singular delta-oriented systems can provide a unified description of singular continuous systems and the singular discrete systems. Here are some notations. I think you are familiar with most of the notations. You may not familiar with the last two. D in the ER means the interior of the region in the complex plane with the center at A0 and the radius R. And the left EA is the set of all finite such as BT SE minus A is 0. And now we consider the problem of admissibility analysis. We consider this system 13. And the definition 1 gives the admissibility definition for the system 13. And in definition 1, there are some definitions for regularity, causality, and stability. They are not given from the physical meaning. In fact, they are given from some necessary and sufficient conditions. For example, the system 13 is said to be stable if this condition holds. In fact, this condition is a necessary and sufficient condition to ensure the stability. So this is what I want to mention. They are not definitive from physical meaning, but from some necessary and sufficient conditions. And from definition 1, we can see that when H tends to 0, then A will tend to AS, and the admissibility of the system 13 will turn to the admissibility of the corresponding singular continuous system. Theorem 1 presents some necessary and sufficient admissibility conditions. There are totally 5 conditions. And the 5 conditions are connected through condition 1. So here, list condition 1. Condition 1 involves a symmetric matrix P satisfies these inequalities. And from condition 1, if we select P in this way, then we can derive condition 5. And if we select Y this way, then we can derive condition 2. And similarly, if we select P in this way, then we can obtain condition 3. And if we select G, satisfying this inequality and the matrix F this way, then we can obtain condition 4. So the 5 conditions are connected together, and the relations among the 5 conditions are now clear. Here are some remarks about theorem 1. When the matrix E is the identity matrix, and the conditions in theorem 1 except condition 4 all become the same equality as this for some positive definite matrix X, which is just the stability condition for the normal third orbital system. And from definition 1, we know that the system 13 of the pair EA is admissible if and only if the pair E transpose is admissible. So to the theorem 1, we can substitute E A with E transpose and A transpose. Then we can also obtain some other equivalent admissibility conditions for the system 13. And now we want to compare our results for SDOS with that for singular continuous systems. Lemma 1 provides an admissibility condition for singular continuous system. It also involves a matrix P. And after comparing, we have a conclusion that it should be pointed out that we cannot use the conditions 1, 3, and 4 in theorem 1 to upload the condition 19 when h tends to 0. For example, if we use the condition 1 in theorem 1 to upload this condition, and we can find that the condition 1 will tend to this inequalities, and the latter one cannot hold because the matrix E is singular. And we analyze this thing, and we think that the reason is as this. The structure of the matrix P in the condition 14 and the condition 19 is quite different. In condition 14, we ask the matrix P to be symmetric, but in the condition 19, the matrix P isn't necessarily symmetric. So I think this is the reason. And now let's see another admissibility condition for singular continuous system, which is given in lemma 2. It is given by the equality 20. And here is the condition 2 in theorem 1. And compare these two inequalities, we can see that when h tends to 0, this term will tend to 0, and A will tend to AS. In this case, the condition 15 will tend to the condition 20. So in this case, we say that the condition 2 in theorem 1 provides a unified admissibility condition for singular continuous systems and singular discrete systems. Now let's consider the problem of admissible control. The purpose is to design a state feedback controller 22 for the system 21, such as the resulting closed-loop system 23 is admissible. And in this case, we call 22 is an admissible controller for the system 21. And here, K is the gain matrix to be determined. Theorem 2 is based on the condition 2 in theorem 1. It provides a necessary and sufficient condition to the problem. And we also gave the design method of the matrix K. Theorem 3 is based on the condition 3 in theorem 1. It only provides a sufficient condition. It also gives the design method of the matrix K. Why the theorem 2 is necessary and sufficient, but theorem 3 is only sufficient, is that in theorem 2, the matrix V1 is positive definite for any positive scalar A. But in theorem 3, the matrix V2 isn't positive definite for any positive scalar A. So this is the reason. And if we add an assumption that EA equals FE to theorem 3, then theorem 3 can also become necessary. But this assumption also have some effects. And this assumption, the admissibility of the closed-loop system 23 means that the system 21 is already regular and causal, and the controller 22 can only change the stability of the system 21. So in this case, the effect of the controller is limited. And it also should be noticed that theorems 2 and 3 are given in the form of matrix inequalities, and which cannot be solved directly through the existing software. So here we present an algorithm to apply theorem 2. And we can also use the similar method to apply theorem 3. Next, we will use another method to solve the same problem. We will use the method of LMI. And first, we rewrite the system 23 in another form, in the form of 26. And the theorem 4 gives a sufficient solution to the problem. It involves some matrices, x hat and y hat, and the x hat and y hat should be of some special structure. And there are also some matrices should be selected in advance, such as D1, D2, and D3. Theorem 4 is based on condition 2 in theorem 1. And similarly, we can obtain theorem 5, which is based on condition 3 in theorem 1. And it also involves x hat, y hat, which have special structures, and D1, D2, which should be selected in advance. And theorem 6 is based on condition 4 in theorem 1. so the slope is similar. And next, we see another theorem. Theorem 7 is also based on condition 2 in theorem 1, but the condition in theorem 7 is a little different from that in theorem 4 because they are based on the same condition in theorem 1, but the form are different. Why theorem 7 have this form? Because we have obtained a unified admissibility condition for singular continuous systems and singular discrete systems. So we want to use this condition, and we have this form. And from theorem 7, we can derive the following result. Assume that when h tends to 0, the system 21 will tend to the following singular continuous system 37. And based on theorem 7, we can obtain theorem 8 directly. We just substitute A to AS, B to BS, and we also don't need this term. So from theorem 7, we can directly obtain the corresponding admissible control result for singular continuous systems. So in this case, we think that theorem 7 provides a unified admissible control result. And here are some remarks about our results. Theorems 4 to 7 have provided line-based substance conditions, and they are obtained at the expense of limiting the structures of some matrix variables, and we can see in the content of the above theorems. And it should be pointed out that whether the LMI conditions have a feasible solution depends directly on the selection of the matrices D1, D2, and D3. For example, we look at theorem 2 and theorem 4. They are all based on the same condition in theorem 1. But the theorem 2 is given in the form of matrix equality, and the theorem 4 is given in the form of LMI. And compare these two theorems, we can see that, in fact, we have converted the difficulty of searching for suitable x, y, and a, satisfying the condition in theorem 2, into the difficulty of searching for suitable D1, D2, and D3, such as the condition in theorem 4 has a feasible solution. And we think the latter is easier for us. Now let's see some examples. First, we consider the system 1 with the following matrices, E, AS, and BS. Then, invisible matrices M and N can be selected as this way, such that MEN has a special structure. And then, we can select a positive scalar as the sampling clearance and set up the Dot operator model of the system 1. We select each to be different values, and we can obtain the resulting matrices A dot and B dot. And we compare A dot, B dot with AS and BS. We can have this conclusion that when x tends to 0, A dot will tend to AS and B dot will tend to BS. Let h be 0.2 seconds, and we adopt A dot, B dot as the matrices A and B of the system 21. Then we can obtain A and B. And this is the system 21. If we let UTK be 0, Then we can derive the enclosed system of the system 21. So we use 13 to express the enclosed system of 21. And consider the system 13, and according to definition 1, we can know that the system 13 is regular total but unstable. And we can also use the conditions in theorem 1 to judge the admissibility, and we cannot find a critical solution. Figure 1 shows the state trajectory of the system 13. We can see that when the time t tends to infinity, the state also tends to infinity. And now we consider the problem of admissible control for the system 21. First, we use the condition in theorem 2. We select x, y, s, and a in this way. Then we can find the condition in theorem 2. Indeed, it's satisfied. And then we know that here exists an admissible controller 22, and the gain matrix P1 can be defined as this. Similarly, we can use the condition in theorem 3 to solve the same problem. We select y, x, s, and a in this way, and we can find the condition in theorem 3 is also satisfied. And in this case, we can define the gain matrix P2 as this. Figure 2 shows the state trajectory of the closed loop system 23 with P1 and P2 respectively. We can find that the closed loop system is indeed admissible. And we can also use the conditions in theorem 4 and theorem 5 to solve the problem of admissible control, and we can obtain K3 and K4. And the figure 3 also shows the state trajectory of the closed loop system with K3 and K4 respectively, and the closed loop systems are also admissible. Next, let's see another example. We consider a 3-UF helicopter produced by Canada Quanser Company. The 3 degrees are the elevator epsilon, its angle c, and travel angle velocity omega. And the linearized dynamic model of the helicopter can be given as the equation 40. Where E1, A1, B1, and UT are given as follows. All the terms in the matrices E1, A1, B1, and UT all have definite physical meanings. You can refer to this part about the specific meaning. This is the picture of the helicopter. It's only for laboratory use. And these are the 3 dynamics diagrams, including elevation dynamic diagram, pitch dynamic diagram, and travel dynamic diagram. And table 1 provides the units and the values of the parameters of the helicopter. In the matrix E1, it involves distance, dt, and ke. And after comparing, we can find that distance is much smaller than the other values in the matrix E1. So we simply select distance as 0, and in this case, U1 becomes a singular matrix, and system 40 becomes the system 1, this form. with E, AS, and BS are given as this. And after we select a positive scalar as the sampling parent, we can set up the dot-orbit model for the system. And we found that A dot is the same as AS, except the element A dot 5, 4. And B dot is the same as BS, except B dot 1, 1 and B dot 1, 2. And these two elements have the same value. So we just observe the values of these two elements. And we select each to be different values, and we can see that when H tends to 0, these two elements tend to 0. And we see AS 5, 4, this is 0, and BS 1, 1, this is 0. So we can obtain that when H tends to 0, A dot will tend to AS, and B dot will tend to BS. Let H be 0.1 second, and we adopt A dot and B dot as the matrices A and B of the system 21, and then we can obtain A and B. And from definition 1, we can see that the pair EA is irregular, no-causal, and unstable, because the four rows of the matrix E and A are all 0 rows. And I have mentioned before that regularity is the condition to ensure the existence and uniqueness of a solution. So in this case, there are in fact infinite many solutions to the unsolved system. And we can also use the conditions in theorem 1. There is no visible solution. And now we consider the design of an admissible controller 22 for the system 21. Since the dimension of the system is 5, it's a little big. So here we just use the condition in theorem 4 to solve the problem. We select S, zhuang, zhu, and zhu3 as this. And we can find that there is a feasible solution to the condition in theorem 4. And this, according to theorem 4, there exists an admissible controller 22 for the system 21, and the matrix P can be given as this. And figure 6 shows the state trajectory of the closed loop system with the matrix P, that the system is indeed admissible. Now we give some conclusion. First, I'll introduce our work. In this report, we have set up the dot-orbit model for a singular continuous system, and then we have presented various necessary and sufficient admissibility conditions for singular dot-orbit systems, and we also have derived several solutions to the problem of admissible control for singular dot-orbit systems. And the value of our work are as follows. First, singular dot-orbit systems can provide a unified framework of singular continuous systems and singular discrete systems. And next, an admissibility result of SDOS can unify the existing corresponding result of singular continuous systems and singular discrete systems. And next, a solution to the problem of admissible control for SDOS can be used directly to solve the same problem for singular continuous systems and singular discrete systems. And finally, thanks for your listening.
Other questions?
So I have a question. How much degree this result can generalize to nonlinear system? Because we only focus on linear system.
Even for nonlinear normal systems, here have no much good result about it. So we first introduce that operator into singular system. We just begin from linear case. Because you know the nonlinear case for normal system also haven't much good results. So the theory about nonlinear case isn't mature.
So what is the general mathematics? So what is the method you use to find matrix M and N to reduce E? Did you use like SVD?
Singular
really?
value.
Yeah, that's what I saw. SVD, yeah.
Yeah.
If you use like a Gaussian elimination something LDU.
No, I don't check.
Okay, yeah. Probably you will create like more zeros.
Singular value.
Yeah. So what's the strategy to figure out J1, J2, J3?
Try.
Try, yeah.
Yeah.
Okay.
To theorem 2 and 3, you also have no way to select suitable X, Y, and A.
Yeah.
So for the case of J1, J2, J3, I also try.
Okay.
Yeah.
Thank you.
Let me make just a quick comment on that. You see, so you can have some take-home message in case you miss something. When there's a linear system, if in the normal case, I think even in the 305, and student can solve the equation because there's a linear equation. You can use the Laplace transform and whatever. But with the singular system, you see when the E in the front, and this make the much difference and challenges. When the E and A has certain relationship, when they omit the solution, usually is not have the solution. But the E and A together, can describe some biology system or an engineering system there. But this is not very, so far the research is not tackled to for example, like Dr. Dongtae, for the non-linear system. Only even in the linear case already present quite challenging situation.
Even for linear singular discrete system, the problem of state feedback haven't been solved. We can only obtain some substance conditions that can be solved by computer. If you want to have some necessary and some conditions that can be solved by computer, we haven't found such result.
Thank you. I'm informed there are refreshments upstairs.
Oh,